we've got here a weight at the bottom. Turn on the axes. The weight starts at the origin, and it's attached to a chain of diene units, which are the polymer repeating unit in rubber, in latex. Those are all bonded to each other at each end in a long polymer chain. There are 7 or 8 of them. And the wiggling that they're doing is because they're at some non-zero temperature. We're gradually raising the temperature over time. You can see the wiggling become more violent. And the weight is rising. The weight is being lifted by this shrinking bit of rubber. There are videos on YouTube where you can see people do of course, the macroscopic version. They have a piece of rubber that you can see in a big weight. You can see the weight also undergoes some kind of Brownian motion while this is going on. So it doesn't go straight up, of course. So we can plot the effective temperature, which is just the time-averaged summed kinetic energy for the whole chain. That's an equation that's set up directly in main and doesn't belong to any component. We can show the equation or part of it in the component properties menu. It's a sum of all of the kinetic energies of the different units of the chain. And then, of course, when we plot that sum, we get an estimate of the temperature. If I instead plot effective temperature on the horizontal axis, and then plot the height of the weight, so the weight's y coordinate, either one of these two, we'll get a nice plot because we'll be able to see what we want, basically the dimensional change in the rubber versus temperature. And the temperature is just some kind of arbitrary units. People talk about entropy. Entropy is the tendency when the chain has a lot of energy for the chain to be displaced sideways somewhere in all different configurations, as opposed to having the chain running straight up and down in real space and have enormous sideways kinetic energies on all the atoms. Alright, thanks for watching.